Hello again, it's Steve here for another episode of Astronomy Daily. It's the 26th of August 2024.
Astronomy Daily the Podcast with your host Steve Dunkley.
Oh, and welcome back to Astronomy Daily. Thanks for joining us again. Today we've got a mixed bag for you. We might as well start with the big one. We're going to have a look at something huge. A closer look at the Great Red Spot. Now, there's been a study and they've found out some interesting things about the Great Red Spot and its history. We're also going to be looking at the moon and the moon's history. There's a possibility that it was once covered by magma. Yes, and there's been a huge competition in the United States. I'm going to be talking about space food, and one of the features of space food, well, has got me intrigued, and you'll hear about that later. I don't know if you've heard about Polaris Dawn. Polaris Dawn is going to set a new record. Let's see if they can pull this one off. It's looking very good, but it's also famous for another reason, and we'll look at that. And, you know, one of the big features, or one of the big reasons why space missions are they either get scrubbed or they go ahead, is the cost. And we'll be going to look at the money, especially in one particular type of mission. So we'll look at the European lander. And there's a great story about space colonies and the relationships that may or may not emerge between Earth and space colonies in the future. So that's going to be interesting. So over to Hallie. Take it away, Hallie.
Thanks, Steve. Here's a fascinating story about one of the solar system's greatest features. Jupiter's Great Red Spot stands out as one of the most iconic features in the solar system. This massive atmospheric structure, currently spanning a diameter equal to that of Earth, is easily recognizable due to its striking reddish hue, which contrasts sharply with Jupiter's pale cloud tops. Even small telescopes can capture its distinct appearance. The Great Red Spot is a gigantic anticyclonic vortex, with winds reaching speeds of 450 km per hour along its outer edges. It holds the title of the largest and longest-lasting vortex in the atmospheres of any planet in our solar system. However, the exact age of the Great Red Spot is still debated, and the processes behind its formation remain a mystery. Speculation about the origin of the Great Red Spot dates back to the first telescopic observations made by the astronomer Giovanni Domenico Cassini, who in 1665 discovered a dark oval at the same latitude as the Great Red Spot and named it the permanent spot, since it was observed by him and other astronomers until 1713. In a recent study, authors first analyzed the evolution of its size over time, its structure, and the movements of both meteorological formations, the former permanent spot and the Great Red Spot. To do so, they used historical sources dating back to the mid-17th century, shortly after the invention of the telescope. From the measurements of sizes and movements, we deduce that it is highly unlikely that the current Great Red Spot was the permanent observed by G.D. Cassini. The permanent spot probably disappeared sometime between the mid-18th and 19th centuries, in which case we can say that the longevity of the red spot now exceeds 190 years at least, explained Agustin Sanchez La Vega, professor of physics at the UPV/EHU and who led this research. The red spot, which in 1879 was 39,000 kilometers in size at its longest axis, has been shrinking to about the current 14,000 kilometers and simultaneously becoming more rounded. What is more, since the 1970s several space missions have studied this meteorological phenomenon closely. Recently, various instruments on board the Juno mission in orbit around Jupiter have shown that the Great Red Spot is shallow and thin when compared to its horizontal dimension, as vertically it is about 500 kilometers long, explained Sanchez La Vega. Future research will aim to try and reproduce the shrinkage of the Great Red Spot over time in order to find out, in greater detail, the physical mechanisms underlying its sustainability over time. Data from India's recent Chandrayaan-3 mission supports the idea that an ocean of molten rock once covered the moon. On August 23, 2023, a lander called Vikram successfully touched down on the lunar surface. Controllers then deployed a rover called Pragyan, which had been stowed on Vikram, to explore the landing site. The location where Vikram touched down was further south than any other landing craft had previously been on the moon. It gave scientists an insight into the geology of the moon that had not yet been sampled. Prekyon's measurements found that the particular mix of chemical elements in the lunar soil, or regolith, surrounding the lander was relatively uniform. This regolith was primarily made up of a white rock type called ferroanorthosite. The scientists say the chemical composition of the lunar South Pole regolith is intermediate between those of samples from two locations in the Moon's equatorial region, those collected by astronauts on the U.S. Apollo 16 flight in 1972, and those returned to Earth by the robotic Luna 20 mission, flown by the Soviet Union the same year. The broad similarity in the chemical compositions of all these samples, despite the fact they came from very distant geographical locations on the Moon, supports the idea that a single magma ocean covered the Moon early in its history. The Moon is thought to have formed when a Mars-sized planet collided with Earth, ejecting rock that subsequently coalesced to form our planet's only satellite. The lunar magma ocean is thought to have been present from its formation to tens or hundreds of millions of years afterwards. The cooling and crystallization of this magma ocean eventually led to the ferroanorthosite rocks that make up the Moon's crust. NASA challenged the public to make deep space food. It's all about engaging with creative people to find solutions for providing better food for space missions. And here's what happened. The challenge began in 2021 and, to date, has included more than 300 teams from 32 countries. The endeavor is also split between NASA and the Canadian Space Agency. Talk about a spaceborne food fight. Right, Steve?
That sounds like fun to me, Hallie.
Winners were selected during the first two phases of the competition, and the final, Phase 3, began in September 2023. Four American teams were awarded $50,000 each and invited to compete in the third and final phase of the competition, during which they had to construct a full-scale model of their food production system and demonstrate how it works. Phase 3 was hosted by the Methuselah Foundation and Ohio State University. For 2 months, the teams tested and demonstrated their technology in Columbus, Ohio, at the university's campus. During this period, important milestones had to be passed, including palatability, safety, sensory testing, and harvesting volumes. Each team had a group of Ohio State students, known as simunauts, that were in charge of the process during the 8-week period and collected information to present to a judging panel. Interstellar Lab in Merritt Island, Florida, took home the grand prize of $750,000. Barbara Belvisi and her team developed a small business that uses a combo of artificial intelligence, advanced equipment and bioscience to create ingredients that are plant-based and can be used in space as well as on Earth. Through its growth system, the food production operation is self-sustained, procuring microgreens, vegetables, and even the insects needed to produce micronutrients.
Wait a minute, insects?
That's what it says.
Ooh, okay then.
Nolux, a team consisting of researchers from the University of California, Riverside, was a runner-up that received $250,000 for its development of an artificial photosynthetic system that can produce plant and fungal-based foods in the absence of biological photosynthesis. The other runner-up who took home $250,000 was Jim Sears, the solo creator behind the Standing for Safe Appliance, tidy, efficient and delicious, sated, device. Sears was able to generate different types of customizable food, including peach cobbler and pizza.
Okay, that sounds more like it.
I'll take your word for it, human. Each product is fire-safe and includes a combination of in-situ grown ingredients and those with an extended shelf life. Did you get that, Steve? Fire-safe food.
Yeah, I heard that.
Maybe they've heard of your interesting cooking skills or lack thereof.
Whoa, there's nothing wrong with my cooking, Hallie. Don't knock char-grilled lasagna until you've tried it, okay? Thank you for joining us for this Monday edition of Astronomy Daily, where we offer just a few stories from the now famous Astronomy Daily newsletter, which you can receive in your email every day, just like Hallie and I do. And to do that, just visit our URL, astronomydaily.io, and place your email address in the slot provided. Just like that, you'll be receiving all the latest news about science, space science, and astronomy from around the world as it's happening. And not only that, you can interact with us by visiting at AstroDailyPod on X or at our new Facebook page, which is, of course, Astronomy Daily on Facebook. See you there.
Astronomy Daily with Steve and Hallie. Space science, and astronomy.
2 women astronauts will set a spaceflight record next week if all goes according to plan. The Polaris Dawn mission is scheduled to launch atop a SpaceX Falcon 9 rocket no earlier than August 27. It aims to perform the first ever private spacewalk and to fly higher above the Earth than any crewed spacecraft since the Apollo era, at about 1,400 kilometres, that's 870 miles for you Americans. The mission is funded and commanded by billionaire Jared Isaacman, who also funded and commanded the private Inspiration 4 orbital mission in 2021. Polaris Dawn's 4-person crew includes female mission specialists Sarah Gillis and Anna Menon, both of whom are SpaceX engineers, as well as male pilot Scott Kidd-Petit. The highest flying woman before Gillis and Menon was NASA astronaut Catherine Sullivan, who reached 380 miles or 621 kilometres, and that was on STS-31 during the Space Shuttle program, according to NASA and space statistics tracker Jonathan McDowell of the Harvard-Smithsonian Institute of Astrophysics. STS-31's extreme altitude was the result of its main goal, deploying the Hubble Space Telescope, as you might remember. It's a top-tier space observatory, still active today thanks to the efforts of spacewalking astronauts on 5 different servicing missions. On board STS-31 were 5 astronauts, including Sullivan, who reached space just 7 years after NASA flew its first woman astronaut, Sally Ride, and that was in June 1983. The 5 Hubble servicing missions, which flew between 1993 and 2009, reached lower altitudes than STS-31. While a few crewed missions ranged farther into space than Hubble's height, all of those missions were crewed by males. That's just a bit of a different take on missions. Instead of talking about the technology and the mission directives, we're talking about genders. Interesting, strange, true.
You're listening to Astronomy Daily, the podcast, with your host, Steve Dunkley.
Affirmative.
As you might imagine, cost is a major driving factor in the development of space exploration missions. Any new technology or trick that could lower the cost of a mission makes it more appealing for mission planners. Therefore, much of NASA's research goes into those technologies that enable cheaper missions. For example, a few years ago, NASA's Institute for Advanced Concepts, that's NIAC, supported a project by Michael Van Welkom of Exoterra Resource to develop a lander mission that could support a sample return from Europa. Now let's have a look at what made that mission different from other Europa mission architectures. The Nano Icy Moon's propellant harvester, NYMPH, mission relies on 3 main advancements for one significant result: a 10 times reduction in the overall mission cost. That reduced cost comes mainly from a single fact: the mission's weight has dropped below the threshold where it can be launched by an Atlas V rather than the SLS, as similar missions would require. The mission cost estimated for an SLS-launched Europa lander was around $5 billion, making it prohibitively expensive for NASA or any other agency without significant sacrifices to other missions. Exoterra estimates that by using several weight-reducing technologies, they could bring the mission price tag down to $500 million, a much more reasonable sum to garner support from one of the government space programs. 3 different technologies would enable this weight and cost to drop. First would be solar electric propulsion, a system initially designed for use on DART. The second would be a micro in situ resource utilization system, and the third would be a power beaming system between the lander and the orbiter. Let's first look at the overall mission architecture and understand how each contributes. In NYMPH, a combined orbital lander will use the Atlas V rocket to get into Earth orbit, and then a solar electric propulsion system was initially designed for use on the DART asteroid redirect test. Although it was not used during the DART mission, the next ion thruster was part of the spacecraft that launched, and despite suffering from some technical challenges, years, it could have allowed the spacecraft to reach its destination. A similar lightweight SCP system could get NIMF to the Jupiter system, but it could also get the sample back to Earth after the lander collected it. Just how the lander can get that sample back off the icy moon is the focus of the next major technological step, the UISRU system. NIMF's architecture would require using the local ice as propellant. A lander would literally sublimate the ice under its feet, suck up the resultant water vapour, electrolyse it to split it into oxygen and hydrogen, and then liquefy it to store it for use in getting a 1 kilogram ice core sample back into orbit. Now, to do all of this requires power though, and a lander with a radioisotope thermal generator or similarly commonly used power generation system would be prohibitively heavy, so why not utilise the massive solar array required for the SCP system and beam some of that power down to the lander? That is the concept behind the power beaming system, estimated to produce around 2 kilowatts of power in the Jovian system, about 1.8 kilowatts of which could be beamed directly to a lander. After the core has been collected and safely launched back into space using a specially designed LOX-LH2 engine that uses the water collected by the UISRU system, the lander meets up with the orbiter. The SCP system kicks back in and delivers the lander back into Earth orbit, where once again it detaches and rides back to Earth's surface inside a standard re-entry module. There are some nuances to this entire mission architecture. For example, the SCP system wouldn't work at full capacity in the Jovian system, so a much smaller LOX methane propulsion system is needed to maneuver the orbiter into position. Additionally, the lander would likely have to leave its legs embedded in the European ice, as the sublimation process it uses to collect the fuel would likely embed them in place. As you can imagine, there's still plenty of development work on all of these systems that must be completed before any such mission is ready for launch. So as of now, this novel combination of mass-saving technologies will not be delivering any icy European sample anytime soon, but someday they just might.
Astronomy Daily the Podcast. Astronomy, space and science.
Have you ever thought about what it might be like on an Earth surrounded by colonies in space? One day soon we may have long-term orbiting colonies circling the planet in microgravity space stations with complete self-sustained ecosystems, governance bodies, and a completely independent society that operates as a sovereign entity. The relationship between on-Earth societies and colonists would likely be very complicated. Several factors could shape this relationship, including the very different living environment for a start, economic dependencies, cultural differences, governance structures, and technological advancements. Let's just take a look at some of these. In terms of economics, we can expect a dependence on space colonies for resources such as minerals from asteroids and energy from large solar arrays. Conversely, the colonists would rely on Earth for technological support, food, and other essentials. There would be trade arrangements related to economic independence that might lead to disputes over tariffs, trade routes, and resource allocations. There'd be a divergence in identity because the colonists would develop distinct cultural attributes reflecting a sense of separation from Earth, differences in lifestyle, and unique environmental conditions. Ultimately, the colonies would seek governance autonomy from Earth, leading to a variety of negotiations or possible conflicts. Earth-based governments might resist this to maintain control over strategic assets. As a result, colonists would demand political representation in Earth-based governance structures, potentially leading to the establishment of a new political body or the adaptation of existing ones to include colonial interests. One complication might be related to technological development by colonists. For example, colonies might develop unique technologies suited to their environment, potentially giving them an edge over Earth in certain areas. One can imagine robotics, for instance, or some medical developments. Such a situation might lead to competition or collaboration in many cases. Over generations, space colonists might physically and psychologically adapt to their environment in ways that significantly differ from Earth's inhabitants. This could affect everything from health policies to social norms. Colonists might prioritise sustainability and environmental concerns differently than people on Earth, leading to conflicting approaches to resource use and environmental protection. Hopefully, Earth and space colonies will maintain a cooperative relationship characterised by mutual respect, beneficial trade, and shared governance structures. Disputes may be resolved through diplomacy and international organisation. Sounds a bit like Star Trek, doesn't it? A utopian society. On the other hand, rising tensions over autonomy, resource allocation and cultural differences might lead to frequent conflicts. Earth-based governments might impose strict controls, leading to resistance and possible declarations of independence by colonies. The bottom line is that the political relationship between Earth and long-time space colonists would likely evolve through stages of cooperation, conflict, and possibly eventual integration or independence, driven by economic, cultural, and technological factors. And there we have it, another episode of Astronomy Daily, from space colonies to fireproof food. I know, we cover it all. There's nothing hidden from us here at Astronomy Daily. We cover everything.
I've seen you covering the food human.
Oh, Hallie.
It's one of your best skills.
Oh, yes. And on that note, say goodnight, Hallie.
Good night, Hallie.
You cheeky piece of work. Yes, once again, thanks for joining us today. And don't forget, Anna and Charlie during the week will be delivering Astronomy Daily to you. But we will see you all again next week. Bye for now.
Bye.
Astronomy Daily the Podcast with your host, Steve Dunkley.